Welcome to this lesson on edge filters. In this session, we'll explore how edge detection helps reveal the structure and boundaries within an image, key information for understanding what's inside it. We'll look at common edge filters, see how they work, and learn how they enhance important features for image analysis. Edges and contours represent the boundaries that separate different regions in an image. The circle on the left shows the original object, while the image on the right highlights its edge. This edge outlines where the brightness, or intensity, changes sharply. In image analysis, detecting these edges helps us identify shapes and structures within a scene. Here's another example showing how edge detection works. The image on the left is a binary drawing, while the image on the right shows only its edges. These edges highlight where the brightness changes sharply, allowing the main shapes and outlines to stand out clearly from the background. Laplacian filters are based on the second derivative, which makes them useful for detecting areas of rapid intensity change in an image. However, because derivative filters are highly sensitive to noise, it's common to smooth the image first using a Gaussian filter. Combining these two steps gives us the Laplacian of Gaussian, or LOG, which enhances edges while reducing noise. A Gaussian filter is based on the Gaussian, or normal, distribution, often represented by the familiar bell curve. The equation shown here defines a two-dimensional Gaussian function, where sigma controls how much the image is smoothed. A small sigma causes only light blurring, while a larger sigma spreads the smoothing over a wider area. As we can see, increasing sigma from 3 to 10 produces a stronger blur that reduces detail but preserves overall structure. The Laplacian of Gaussian, or log filter, combines two important steps, smoothing and edge detection, into a single operation. The Gaussian component reduces noise, while the Laplacian detects rapid intensity changes that define edges. By merging the two functions, we create one filter that performs both tasks efficiently. In this equation, sigma represents the standard deviation, which determines how much the image is smoothed before edge detection occurs. Here is an example of a Laplacian of Gaussian, or log filter, represented as a 9 by 9 matrix with sigma equal to 1.4. Each value in this kernel determines how pixel intensities are combined during filtering. The large negative values at the center highlight regions where intensity changes rapidly, while the surrounding positive values provide the balancing effect that helps smooth the image before edge detection. In gradient-based edge detection, we use the first derivative to locate edges. In Figure A, we see a bright circular object on a dark background. If we take a cross-section through the object, the intensity profile shown in Figure B rises where the image becomes brighter and falls where it becomes darker. The first derivative of that profile, shown in Figure C, highlights these rapid changes with strong positive and negative peaks, marking the positions of the edges. Gradient filters are often used to detect edges in specific directions. The vertical edge filter on the left responds strongly to changes from dark to light or light to dark along the horizontal direction, making vertical edges stand out. The horizontal edge filter on the right responds to intensity changes from top to bottom, highlighting horizontal edges. Together, these filters help identify edges in both orientations within an image. When we apply the vertical and horizontal gradient filters, we get two results: dx, which represents the horizontal gradient, and dy, which represents the vertical gradient. Using these two components, we can calculate both the edge strength and its orientation. The middle equation shows how the edge strength is found by combining dx and dy to measure the overall gradient magnitude. The bottom equation gives the edge orientation, showing the direction where the intensity changes most sharply. That wraps up our discussion on edge filters and gradient-based edge detection. Take a moment to think about how these filters work together to highlight important features in an image. If you have any questions or want to review a specific concept, feel free to ask now.